Can you recognize what that yellow substance is? Actually, that's a pickle, and they put electricity through it. There's sodium in the pickle. The electrons go from ground state to excited state, they fall back down, give off that characteristic yellow color when they go to ground state. Wavelength of 589 nanometers, which goes with the yellow light that you see when you do sodium either in a pickle or flame tests. So first, what is ionization energy? Well, first of all, we're creating an ion and we're putting energy in to do that. It's the amount of energy required to remove an electron from the ground state of a gaseous atom or ion. Now that electron that removed is the first one, is the energy that's required to remove that first electron. Now that first electron is the one that is of highest energy if you were to write out the entire electron configuration. The second ionization energy is to remove that second electron that is at the, so ionization energy. Let's look. What we're going to do is look at aluminum, and we're going to take it through successive ionization energy. So we start with a neutral aluminum atom, add in, and then it's the amount of energy that's required to remove that one electron. So that's I1 as the first ionization energy. The second ionization energy is always going to be higher because, first of all, there's a charge. Aluminum is now charged, so you're removing a negative electron from a positive aluminum atom. And also, 3p, from which you're removing that electron, is going to be a little bit higher energy than the 3s. The first electron in aluminum is removed from 3p, and now we're removing it from 3s, and the 3p is a little bit higher energy, so that's easier to remove an electron from higher energy. This electron right here is going to be removed from 3s, which is a little bit lower than the 3p, so that requires a little bit more energy. And also, the next electron is removed from a 3s as well, but notice more energy is required because there's more protons, and it's also removed from a positive atom. Then there's a huge jump in energy because we're removing an electron from a 2p orbital. So this is a core electron, so it's much closer to the nucleus. So a huge amount of energy is required to remove that next electron. So this big jump in energy is something we're going to look for whenever we go to core electron that's removed that is closer to the nucleus. You see in this chart, there's a difference between the inner shell or core electron removal versus any of the valence shell electrons. We notice we just looked at aluminum. Another thing you might notice here is notice how ionization energies increase as we go across a period. Sodium and argon are all in the same period. What is different as you go across a period is we're increasing effective nuclear charge. We're adding protons, so those electrons are held in much tighter, so it takes more ionization energy to remove all those electrons. So it requires more energy to remove each successive electron, and there's a huge jump when you go from a valence electron to a core electron. Next, so would you expect a greater ionization energy for the first ionization energy for boron or the second ionization energy for a carbon atom? The second ionization energy for a carbon atom is actually greater. Now, one reason you might look at this is if you think of boron. Boron is 1s2, 2s2, then 2p1. And so this is the electron that's removed for the boron. But if you remove an electron from carbon, the carbon's electron configuration is 1s2, 2s2, then 2p2. Now notice that electron for the second ionization energy for carbon is removed from this level as well. But the difference is the number of protons. Carbon has one more proton than boron, so that second electron is going to be held in much tighter, so it's going to require a lot more ionization energy. So trends in first ionization energy. We actually mentioned one of these already. That would be the family or column trend. Ionization energy increases as you go up a family. Now the reason being, these electrons, this valence electron, as you go in this direction for every single column, is going to be located closer to the nucleus. Closer to the nucleus, the greater the pull, the greater the ionization energy. As you go the opposite direction, ionization energy, because that valence, that outer electron, is much further from the nucleus. The further away it is, the less energy that's required. The other trend we also mentioned as well, because we looked at the period of sodium all the way over to argon. Notice that ionization energy generally increases as you go to the right. And the reason for that is you have an increased effective nuclear charge going to the right. So going to the right, ionization energy increases, and going up a family, ionization energy increases because those atoms are smaller. That's just basically what I just said. Next, now there's a couple discontinuities. Generally, as you go across the row, it gets harder to remove an electron. So as you go to the left, as you go left to right, effective nuclear charge increases. And as you go, and also the atoms or the electrons' distance from the nucleus decreases as well. So two reasons ionization energy increases going to the right. So trends in first ionization energy, there are two apparent discontinuities in this trend. Now the first discontinuity is between groups 2A and 3A. And that you see here with beryllium and boron. Now the fact is it's much easier, generally it's more difficult as you go to the right, but with 3A it's actually easier. So why is it easier when you go to the right for this one than it is, and why does this trend not work for just 3A? It's easier for 3A than it is for 2A. Now the reason it's easier for 3A is that those two s electrons actually shield that 2p electron a little bit. And so since they do a little bit of shielding, it's easier to pop off that 2p electron. The electron removed from the 2p is a 2p orbital rather than a 2s, and it's a little bit further away. And also there's a little bit of repulsion or shielding from those s electrons that are in that level before. So that's true for boron, aluminum, gallium, all those we'd expect, generally following the trend, that the ionization energy would be higher for 3A, but it's a little bit easier because it's a first electron in that p orbital, it's further from the nucleus, and there's a little bit of repulsion from that doubly paired s orbital that's right before it. The second discontinuity, now this one we've alluded to as well, that occurs in between 5A and 6A. Now following the trend, we expect 6A to have a higher ionization energy, but it generally does not. So it's easier, once again, with 6A. Now why is it easier with 6A? The reason being, when you go to 6A, those electrons that are removed come from a doubly occupied orbital. Anytime there's two electrons in an orbital, they actually experience a greater repulsion, and so it's easier for that electron to be removed. So let's look at a question. Which of the following have the highest ionization energy? So we're going to look at all these atoms. We've got carbon, nitrogen, oxygen, and then we have aluminum and silicon. Now first of all, we'd expect as atoms get further away from the nucleus, or electrons get further away from the nucleus, they have a lower ionization energy. So for that reason, we're going to go ahead and disqualify aluminum and silicon because they are in the third row, and so that would be a 3p orbital. So those are going to be a little bit easier to remove than a 2p. Next, we're going to go this 2p level and see which one of these is going to have the highest ionization energy. Well, generally we know that ionization energy increases as you go to the right. So if we just follow the trend, we pick oxygen. But hopefully you remembered that this is one of the places you have a discontinuity. In this one situation, 5A is actually greater ionization energy than 6A. Now why is that? Now if you remember, we talked about a doubly paired orbital. For nitrogen, all these electrons in 2p are single. But in oxygen, that one electron that would be removed is from a paired orbital. And for that reason, oxygen is easier to remove and has a lower ionization energy because it's easier to remove this one doubly paired electron than it is a singly paired electron from nitrogen. And for that reason, nitrogen would have the highest ionization energy for two reasons. One, it's closer to the nucleus than aluminum and silicon. And second, in that period, it has the greatest effective nuclear charge of all the things that are in the row, and it's not doubly paired, and so it's a little bit more difficult to remove than oxygen. And so the correct answer for that was nitrogen. So which one of these would have the largest ionization energy? Now remember, ionization energy increases with each successive ionization energy. So we have the second ionization energy of sodium, we pick that out of all the sodiums, and the third ionization energy of magnesium. Now notice for each one of these, it's the first time we're going to be removing a core electron. So which one do you think would be greater? I would pick magnesium because magnesium actually has 12 protons, which means it has a greater pull and a greater nuclear charge than sodium. So I think magnesium would be the best choice for this one, or for that third ionization energy, and that actually is the answer. Nice job. Let's get going. Would chromium 3+ or vanadium 2+ have the same or different electron configurations? So let's start with the configuration of the neutral atom. There's chromium and there's vanadium. Now what's different from these? If I take 2 electrons or 3 electrons from chromium, the electrons are going to be removed are always the valence electrons, and that would be the 4s first, And then if you take 3, you're going to take one of these 4s, and then that's going to be 3d3. So the electron configuration for the chromium ion is going to be argon in brackets and then 3d3. For vanadium, you're only going to remove 2 electrons, and so that's going to be removing those 4s2. So its electron configuration for vanadium 2+ is going to be argon in brackets and 3d3. And so they both have the same electron configuration of argon in brackets 3d3. Next one. Last, we're going to talk about electron affinity, and that's an energy change that's accompanied when you add an electron to a gaseous atom. So basically, it's the opposite of ionization energy. So if you were to ask for the value of ionization energy of chloride ion, what is the relationship between that and the quantity of electron affinity for chlorine? So those should be equal in magnitude but opposite in sign. So trends in electron affinity. In general, electron affinity is the same as ionization energy. It becomes more exothermic as you go from left to right. So it's generally going to increase as you go this way, and also increases as you go up a column because those atoms are closer to the nucleus. Now there's a couple of discontinuities. The first one is between when you go from the beryllium or the beryllium, and you'll see that there. So the first one is group 1A and 2A. And the reason it is much lower is because when you're adding an electron from beryllium, you're actually going to be adding that electron in a 2p orbital, not a 2s. And the 2p is actually further away from the nucleus, and it feels a little bit of repulsion from the 2s. So similar to what we talked about with ionization energy. And then the other discontinuity you see is between groups 4a and 5a. And that time the light electron must go into occupied orbital, p orbital, and there's a little bit of repulsion. So based on the periodic trends, which of the following elements is expected to have the largest, most negative electron affinity? So you got potassium, sodium, silicon, and sulfur. For this, sulfur is going to have the most negative electron affinity, because you can see from the list that silicon is located right here, and then we have sodium, and then we have potassium. So notice, remember, electron affinity increases as we go to the right, and sulfur is farthest to the right, and it also increases as we go up a family.